Good evening everyone, welcome to Gate Academy Global. So our today's session is also based on random variable and random process. So as we have discussed in the last session, random variable and the random process in that previous session. So today is the last session for the random process, and now that I will jump to the amplitude modulation. Okay, so let's wait for the other students to be connected. So in the last session, as I told you that random variables, I covered the complete portion of the random variable. So today we are going to discuss about the random process. So let's wait for a few students, at least few students can come. Right now we are having very less student. Good evening Shubham. So today we are going to discuss random process. Okay, so I hope you have revised the random variable and random process. So today will be the last session for the random variable and random process. Good evening Anand and good evening Vivek, Hari. Acha, mera rank, oh, sorry, my rank. What will you do with my rank? Well, I can tell you my rank. My rank was 698 in GATE 2008. And I have done MTech from IIT Guwahati, if you don't know about it. So you may see my profile from the GATE Academy site. Okay, Vivek. So I had done MTech from IIT Guwahati in signal processing. Good evening everyone, Lokesh, Rahul, Vijay. So now we are having 15 plus students. So now we can start with the questions. Okay. Thank you, Yash, but I don't feel so. I don't feel so actually. I am looking for more fit actually. Good evening, Rohit. So are you all ready for the question? Are you all ready for the question? No, not for the six pack actually. Best book for communication system is you can follow any standard textbook like BP Lati, Simon Hekin and Prokis, and these are the standard books that you can follow, right? And there are actually many materials you can get, and in every book the different topics are very good. So that's why we cannot say which book is good, but you have to follow the different textbook for the different topics. And thank you Rishabh. And the best book for the signal and system, you can ask Neeraj sir. Well, the best book is nothing but the Oppenheim. We always used to say that Oppenheim is the best book for signal and system. If you are having the PD course, so start with the basic subjects like network or digital, which is not depending on the any other subjects. Okay, because if you suppose study the communication, then for that you should have a good knowledge about the signal. So that is why you can start with the network or digital or maths. These subjects are the quite basic subjects which we will be using in the other subject as well. Oppenheim is hard, and so you can follow the Neeraj sir lecture, and you will be having a good idea about the signal system. He has covered the signal and system very vast, in fact in very detail in his PD course as well as in the GATE Academy Plus channel. Okay, so let's start with the question. So we are having the 20 plus student now. So the question number 1, let's start with the question number 1. So question number 1, we have a wide sense stationary random process x of t is applied to the input of an LTI system with impulse response h of t equal to 3 into e to the power minus 2t ut. If the mean value of x of t is 2, then the mean value of output yt is. No, bits per channel cannot be the capacity. I don't think so. The channel capacity cannot be bits per channel. So first answer we have got, that is 3. Yash Raj has got the answer 6. So we are having 2 different answers. So let's see what will be the correct answer. So we are having the 2 common answer, and Manku is getting the 5. So Vivek Sharma is also getting 3. Ketan, welcome Ketan again. You are getting the answer 6. Okay. So let's start with the solution. So here we are having the first basic question from the random process. We are having the wide sense stationary random process. So suppose there is a system, suppose there is a LTI system, and for this system, if the input is random process x of t and the output is another random process y of t and the response of the system is h of t, then for this system we can write the expectation, that is the mean value of output random process, is equal to h of 0 expected value of x of t. Okay, so this is the first relation that we can write, and the another relation we can write is the output power spectral density Sy of f is equal to h of f magnitude square Sx of f. So this is the relation between the output power spectral density and input power spectral density, and this is the relation between the output mean and input mean. So you can see here I have written the capital H, that means it is nothing but the Fourier transform of h of t, the Fourier transform of h of t, and that is nothing but h of f. So we know that the Fourier transform of h of t is h of f, right. So we have to calculate the Fourier transform of h of t and substitute the f equal to 0 in that expression. Okay, so we are having 3 into e to the power minus 2t. Okay, so this is e to the power 3 into e to the power minus 2t ut. So the Fourier transform of this, here it is ut. So the Fourier transform of this is nothing but 3 upon 2 plus j 2 pi f, or j omega you can write. So this is the h of f. So the value of h of f is 3 upon 2 plus j 2 pi f, and at f equal to 0 you will get capital H 0, this is 3 by 2. So now when you substitute the value in this expression, you will get the expected value of y of t is equal to h of 0, which is 3 by 2, and the expected value of xt is 2. So you will get the expected value of yt as 3. Okay, so this is, remember that this is nothing but the value of transfer function at f equal to 0, that is Fourier transform of the impulse response of the system. So if you substitute the t equal to 0, if you substitute here t equal to 0, you will get h of small 0, and that is the value 3, and in that case you will get, this is 3 and this is 2, so 3 into 2 you will get 6. Okay. So if you directly calculate h of 0 from the given expression, that is at t equal to 0, then this will be 3 and this is 2, so then you will get the answer as 6. But here you have to remember that this is the formula where capital H of 0 is used. Okay. So it is nothing but the transfer function at f equal to 0, so the correct answer would be 3. You cannot substitute h of small 0 here. Okay. So those students who have got the answer 6, I think they have done the same mistake, because if you substitute h of 0 directly in the given impulse response, in that case you will get answer as 6. That happens, you are saying the same thing, Ketan, that you have substituted the value at t equal to 0. You have to remember that in the Fourier transform we have to substitute f equal to 0, not t equal to 0. So the good book for the random process, you can see there are many books again for the random process. There is no standard book, but the Peebles Junior, you can write the name of the book is Peebles Junior for the random process and random variable. This is the good book for probability, random variable and random process for the communication system, Peebles Junior. Okay. So let's solve next question. Question number 2. So question number 2 is, suppose that a wide sense stationary random process x of t with power spectral density Sx of omega is the input to the filter shown in figure. The power spectrum density of the output process y of t will be. There are 4 options given to us. So you can join our Telegram group. We have given the link above, so you can join the Telegram group and you can directly connect with me. So in question number 2, we are having a system given, and input to the system is the random process x of t whose power spectrum density is given, and the output random process is y of t. We have to calculate the power spectral density of output. As I told you in this question, if there is a system and input is x of t and output is y of t, we can calculate the output power spectrum density by using h of f magnitude square Sx of f. So that means you have to calculate Sx of h of f mod square. So Manku is getting answer as B. So we are having the system like this. This is plus and it is given as minus. This is delay by t. This is x of t and this is y of t. So first of all we have to calculate the h of f. Okay, so this is the complete system. This is the complete system, and input to this system is this x of t and output to this system is y of t. So the relation we know that the output power spectral density is related with the input power spectral density by h of f magnitude square. So first of all we have to calculate the h of f. Okay, so the gain of this path is 1 and this is the delay element. So the transfer function for the delay element is given by e to the power minus j omega t. Okay. So the transfer function for the delay element is given by e to the power minus j omega t, and this is having 1. So we are having h of f equal to, this is positive, so 1 is positive, and this is negative, so minus e to the power minus j omega t. So we are having the different answer. Vaibhav is saying C, Shubham is also getting answer B. Okay, so this is h of f. So h of f can also be written as 1 minus, this can be written as cos of omega t minus j sin omega t. Okay. So what will be the magnitude? So let's separate the real part and imaginary part. So this is 1 minus omega t, and this will be plus j sin omega t. So this is h of f, or you can say h of omega. So now we have to calculate its magnitude square. So h of omega magnitude square, okay, because this is in terms of a function of omega, so that's why I am writing as h of omega. So this is 1 minus cos of omega t whole square plus sin of omega t whole square. This is the real part square and imaginary part square, and we should have the root over it, but because we are writing h of omega magnitude square, so there will be no over root. Okay, so this is 1 minus 2 cos omega t plus cos square omega t plus sin square omega t. So cos square omega t plus sin square omega t become 1, 1 plus 1 is 2, so we can take the 2 common and we get 2 into 1 minus cos omega t. So this is h of omega mod square. Now we had to write the power spectral density of output, or Sy of f, or you can write Sy of omega. This is h of omega magnitude square into Sx of omega. So you have got the answer 2 into 1 minus cos of omega t and input power spectral density. Okay, so according to this, the correct answer would be option C, right. So those who got the answer as option C is the correct answer. Okay, is there any doubt in this question? Okay, so why did you get the answer as B? Manku, your answer was B, but the correct answer is C. So what mistake you had done? May I know what was the mistake? Okay, so the question is how I took this delay e to the power minus j omega t. So let's coming to this point. So suppose there is a system, okay, and this is a LTI system, and the response is h of t, and input is x of t, and output is y of t. Is it okay? Now what is y of t? If you want to write y of t, then what is the value of y of t? So the y of t is nothing but x of t convolve with h of t, isn't it? So if I take the Fourier transform, okay, so taking Fourier transform, we get y of f is equal to x of f into h of f, and this h of f is nothing but the transfer function, and it is y of f divided by x of f. Okay, okay, Hari, is this clear to you? Now in this question we are having a delay element and it is delayed by t. So this is the input x of t and this is the output y of t. So what is the meaning of this delay? So if you delay the signal, what you will get? So here you will get x of t minus t, this is nothing but the delayed by the t second. So we are having y of t is equal to x of t minus capital T. So if I take the Fourier transform again, so y of f is e to the power minus j 2 pi f t and x of f. This is how we calculate the Fourier transform of the delayed signal, or it is known as the time shifting property. Time shifting property of Fourier transform. Okay, because it is delayed by the t seconds. So if you write the Fourier transform of it, so this is the time shifting property of the Fourier transform. So now y of f and x of f you have got. So if I want to calculate h of f, so h of f is nothing but the ratio of y of f to the x of f, which will be equal to e to the power minus j 2 pi f t, or you can write e to the power minus j omega t. Okay, so the transfer function for this delay circuit is e to the power minus j omega t. This is how we got the answer. Okay. Okay, so it is clear to you, Hari. So let's move to the next question. Question number 3. Question number 3 will be showing on your screen. Solve that question, and we are using the same concepts that we had studied in the first and second session. As I told you that I am not taking any tough question, or in fact very tough questions that can be asked in the random variable, that will be done later on of this year, because when it is gate will be close to you, so that time we will solve. So that would be more beneficial for you, because if we solve this now, you may forget the concept. So that's why we are right now taking the basic questions that will be useful for any subject, or to have a good command for this subject. So the variance, Abhishek, Nupur is getting 6 and Abhishek is getting 4. We have to calculate the variance. Abhishek, see the question carefully. In this type of basic question, you should not do the mistake. Nupur and Abhishek, check your calculation. We have to calculate the variance. So I have got the answers as 6, 4, 6, 4, but all the answers are wrong. 6, 4, minus 10, all the answers are wrong. Check your calculation, or check the property that you are applying to solve these questions. So Ketan and Shubham is getting the answer, which is 2. So the correct answer for this question is 2. Okay. So the answer for this question will be 2. And how do we get this? So we are having a wide sense stationary process, and the autocorrelation of this process is 4 tau square plus 6 divided by tau square plus 1. Okay. So let's write few properties that is useful for you. Property of autocorrelation, I am writing in short, property of Rx tau. So the first property that you should know is autocorrelations are always a even function. Okay. The autocorrelation is always an even function. It always follows the even symmetry. So if you substitute tau is equal to minus tau, you will get the same function. So that's why it is following the even symmetry, and that is why this is the valid autocorrelation. So if it is valid autocorrelation, we can apply the different property of autocorrelation. And another property is Rx tau is always less than equal to Rx of 0. This is the second property of autocorrelation. At 0 we will get the maximum value, and in other value we may get the value equal to 0 or less than that. Third one is Rx 0 is called power of the process, or it is equal to mean square value. Mean square value means the power, total power. Okay, so Rx of 0 we get the power of the process and mean square value, and mean square value means expected value of x squared t. This is the mean square value. And the fourth property is we can also calculate the DC power, or it can be written as the mean whole square, that is limit tau tends to infinity Rx of tau. Limit tau tends to infinity Rx of tau, you will get the mean whole square. So now we are having the many answers and they are answering as 2. So the mistake you have got, okay, so that's why you are getting the correct answer. So according to these properties of autocorrelation, if I want to calculate the variance, so we know that the variance equal to mean square value minus mean whole square. Okay, so we have to apply the third and the fourth property. In the third property we are going to get the mean square value, and in the fourth property we are going to get the mean whole square. So here at tau equal to 0, so if I substitute tau equal to 0, we get the mean Rx 0, mean square value, and this is the mean, which is limit tau tends to infinity, and it is 4 tau square plus 6 divided by tau square plus 1. Okay. So when I substitute tau equal to 0 in this expression, that is the autocorrelation, we get 6 minus, when tau tends to infinity we have to take the tau common, tau square common. So it will be 4 divided by 1 here, and this will be plus 6 upon tau square and 1 upon tau square. So if you write like this, this is 4 plus 6 upon tau square divided by 1 plus 1 by tau square. So when tau tends to infinity you will get 4, so the variance is 2. Fourth property you forgot, Manish, so you should not forget, or if you are forgetting, so that is why we are having this session, so that you can recall what you are not remembering, you are not able to remember for a long time. For that you should attend this type of sessions, because this type of session is nothing but a recall for the properties or the formulas that you can forgot. Okay, so this type of session will be very helpful to remember all those formulas that you may forget. Okay, so next question, question number 4. Solve question number 4. Hello Yogesh, welcome to this session. So solve this question. Question number 4 is saying that determine the missing elements denoted by A, B, C, D and E in the following autocorrelation matrix of a wide sense stationary random process y of t. We are having one autocorrelation matrix and we have to find the missing terms. So answer in one line, okay. If you get the answer of A, B, C, D and E, then write in the single line what you are getting value of A, B, C, D and E. Anand Gaurav, tell me the answer. If you are having the correct approach, then you should answer it. B, you are getting 1.3. Okay. Manish, try to answer it in a single line so that I can see, because if somebody else will answer, then your answer will be go above. So try to answer in a single comment. No idea about the autocorrelation matrix. There is nothing special about the autocorrelation matrix. That is same concept as the normal autocorrelation, but the way to write it is different. I will come with some theoretical part when I will come, then I will discuss this part also, because I know this is a bit different for you guys, because you have not seen the autocorrelation matrix anywhere, I am sure about it. So that's why I have kept this question to make you learn how to solve or how to answer. So Anand Gaurav is 0.9, 3, 2 and 1.1, and you have forgot one answer, I guess. 1, 2, 3, 4. I have asked 5 questions, 5 elements. So the order is 0.9, 1.3, 2, 1.2 and 2 and 1.2. No. Abhishek, I think there is something which you are missing. Check once again. There is one answer that you are missing. One value is incorrect. Abhishek, your one value is incorrect, others are correct. So what is that value? Check once again. Follow these properties. Ketan, follow this property, you will get the answer. Yes. Abhishek, now you are correct. The sequence. No. Sorry. D is also incorrect. D is also incorrect again. D is 0.8. Yes, Anand. D is 0.8. Abhishek, check your answer. D should be 0.8. Okay. Now you have got the answer. Okay. So those students who are having some idea how to apply can answer it, and this is nothing but based on this property, that is the even symmetry. Okay. So it follows the even symmetry. So because of that, hello Preeti, so because of that the matrix should be symmetric. So how do you get the symmetric matrix? So it means that 1 2 should be equal to 2 1. Okay, R12 should be equal to R21. So R21 is B and the value of B will be 1.3. Okay, similarly we are having the value of A, right? So the value of A is R14. So R14 will be equal to R41 and R41 is the 0.9. Similarly we are having C, which is R33. So R33 will be, because the diagonal element it is equal to 0. Okay, so this is the value C. The diagonal element should be equal to, at tau equal to 0 actually. Okay, so at tau equal to 0 we should have the value as 2, and R42 is equal to R24, and according to that this will be 0.8, and similarly R23 is equal to R32, which is E, R42. In fact this is R43, so it is equal to R34, which is the value of E, which is 1.1. So this is how you get the value of the missing element. Okay, the diagonal elements, remember that the diagonal element shows that the Rx 0. Diagonal element shows the maximum value. You can see that all the other elements are less than the diagonal element. Diagonal element is 2 and all the other elements are less than diagonal element. So the diagonal element is actually representing this one, Rx of 0. Rx of 0 is always greater than the Rx of tau. For other value of tau, you will get the value which is less than 0 or equal to 0. So what is the significance of principal diagonal? As I told you that the principal diagonal is showing the mean square value of this process. Okay, Abhishek, is it clear to you? When I will discuss the theory, so you will see how do we write this matrix, and according to that you will get this. But here we are having the basic property, and that is the symmetrical property, and how this matrix can be symmetrical, and according to these values we will get the symmetrical matrix. Okay. So next, coming to the question number 5. So question number 5 is, a stationary random process x of t has the power spectral density Sx of omega is equal to 24 divided by omega square plus 16. The mean square value of the process is. Thank you, Ketan. Now we are having question number 5. Solve that question. So we have got the answer, which is 4.71 and 4 by 6. Sorry, both of you are wrong. Solve it correctly. Another answer I am getting, Yogesh, that is 6, that is also incorrect. Check it properly, check your calculation properly. A stationary random process x of t has the power spectral density Sx of omega is equal to 24 upon omega square plus 16. Mean square value 6 pi. (4.33). Weber is also getting 3. 4 again, no. 4 is the wrong answer. (18.84) is another, again wrong answer. 1.5 is also wrong. Ketan and Abhishek has got the answer, and Weber as well. The correct answer is 3. So check once again. If you are getting 3, then it is okay, else you are doing some mistake. Okay, so check your calculation till I write the property of power spectral density. Okay, so property of power spectral density, it is Sx of omega is real and it is always greater than equal to 0. Second property is it also follows the even symmetry, so Sx of omega is equal to Sx of minus omega. Third property is area under power spectral density gives power of the process, power that means mean square value of the process. So how can we calculate the area? So we can calculate the area by integrating the power spectral density Sx of omega d omega. This is the mean square value or power. And if you are writing omega, remember that if you are writing in function of omega, then it is 1 upon 2 pi integration minus infinity to infinity Sx of omega d omega. Or if you are writing in terms of f, function of f, and integrating with respect to f, then it is minus infinity to infinity Sx of f df. Fourth property that you should remember is the Fourier transform of autocorrelation is power spectral density. That is known as Wiener-Khinchin relationship, and according to this relationship, the autocorrelation function and the power spectral density are Fourier transform pair. So there are two methods to solve it. Okay, so there are two different methods. One we can calculate by using this property, where we have to take the inverse Fourier transform to get the autocorrelation, and we know that the autocorrelation at 0 is equal to power of the process or the mean square value. As you can see that we have to calculate the mean square value. So the mean square value is nothing but autocorrelation at tau equal to 0. So for that you have to get the autocorrelation first, and autocorrelation we can calculate by power spectral density by taking the inverse Fourier transform. So if we take the inverse Fourier transform and substitute tau equal to 0, you will get the power. Okay, and another process is to calculate the area under the power spectral density. So area under the power spectral density is 1 upon 2 pi integration from minus infinity to infinity Sx of omega d omega. Okay, so let's solve by these two methods. So mean square value is 1 upon 2 pi integration minus infinity to infinity Sx of omega d omega, or we can also write, because this is an even function, we can write 2 times of 0 to infinite Sx of omega d omega. So this will be 1 upon pi integration from 0 to infinity. What is the value of Sx of omega? This is 24 upon omega square plus 16 d omega. So we can write 24 divided by pi, this is 1 upon 4 tan inverse omega by 4, limit from 0 to infinity. Okay. So this is 24 upon 4 pi, and when we substitute infinity we get pi by 2, and when we substitute 0 we get 0, so we will get the value as 3. So this pi and pi will get cancelled, this is 24 divided by 8, which will be 3. So this is how you can get the mean square value. Okay. So is this method is clear, or this integration is clear to you? Now let's solve by the fourth property. Okay, so by fourth property, how can we write the inverse Fourier transform of this process, this power spectral density? So this is e to the power minus a mod tau. If you know the Fourier transform of this is the standard function e to the power minus a mod tau. The Fourier transform of this is 2a upon a square plus omega square. Now we are having this is 24, so we are having 24 upon 16 plus omega square. So this should be 2a. So let's write in the form of 2a, where what is value of a? So let's write it again. This we can write as 4 square plus omega square. Okay. So we are having 2 into 4, that is 8, and this is also 3. Okay. So 24 can be written as 4 into 2 8, 8 into 3 is 24. So this is 3 into 2a upon a square plus omega square. So what is the inverse Fourier transform of this? This 3 is constant, so this 3 is multiplied here, and this is 2 into a. So it becomes e to the power minus 2 mod tau. Is it okay? This is how we can write 3 into e to the power minus a mod tau. Uday, Okay, so you have got this value. So this is how we can write this 24, and if the 24 is divided into this form, so this is 2 into a upon a square plus omega square. The extra term constant 3 is multiplied. So in both sides we have to multiply it by 3. So here I have multiplied it by 3. So we have got the value of autocorrelation, which is 3 into e to the power minus 2 mod tau. Okay. So at tau equal to 0 you will get the mean square value, and the mean square value is now 3. So in both the method you will get the answer, and both the method are easy. So whatever you you feel convenient, you can solve it by that. A is 4. Okay. Abhi a is 4, that I have already written here. So all of you have got the answer. A is, I have written, this is 2 into a, this is 2 into a, and this is a square plus omega square. A is 4. I am also saying a is 4 only. Okay, Abhi, clear? Okay, everyone has got the answer? So are you ready for the next question? So next question, question number 6. Okay, Manish, Uday, Hari, solve the next question, question number 6. We are having the total of 12 questions today. Hello Vishwanathan. Why you are late today? Manish is getting the answer as 0.5. Hello Pratik. So you guys are coming late. Yogesh is getting answer as 1. Shubham is also getting 1. Zero point five, Preeti 1. So that means the answer may be a 0 or 0.5 or 1. Just return from the college, okay. What is the timing of your college, Vishwanathan? That's why I am taking the session from the 7 p.m. because I thought that many of you are college going, as we talked in the last class, last session, that many of you were saying that you guys are college going. So that's why I kept my session from the 7 p.m. so that you can return from the college and can join the session. Manish, your answer has been changed from 0.5 to 1.5. Actually, the 0.5 is the correct answer. So 0.5 is the correct answer. Okay, you are from IIT Madras, so today there was a delay. Okay, intern in IIT Madras. Okay. So next is question number 6. So this is the power spectral density given for a random process. This is Sx of f, and there is a impulse at f equal to 0, and the magnitude is 1 here. So we have to calculate the AC power, and here this is the autocorrelation. If I find the autocorrelation, then we also know that the variance is equal to mean square value minus mean whole square. Okay. So here variance is known as AC power, and the mean square value I had written here the power, which is total power, and the mean whole square I have written here is as DC power. So this is DC power. So we have to calculate the total power and the DC power. So if you calculate the total area, you will get the total power, but to calculate the DC power, you can easily calculate it by calculating the autocorrelation. Okay, so we know that from the fourth property, the autocorrelation and the power spectral density are Fourier transform pair, and from the autocorrelation we can get the total power as well as the DC power. So let's calculate the autocorrelation. So we can take the inverse Fourier transform. So taking inverse Fourier transform, we get Rx of tau, which is the impulse at 0, that means there will be some constant, because the Fourier transform of any constant is impulse. So Fourier transform of the constant 1 is impulse, plus the height is 1 and the intersection with the f axis is f naught. So this is 1 into f naught, so this is f naught, and sinc square, you should know the Fourier transform of the triangular signal is sinc square, and the Fourier transform of rectangular is sinc function. So that's why I am writing directly, because this is a standard pulse for which you can directly write the Fourier transform. So this is we are taking the inverse Fourier transform because we are applying the duality property. So this is sinc square f naught into tau. So this will be the inverse Fourier transform of this signal. There are two different signals, one is the impulse signal and another is the triangular signal. For the triangular signal we will get the sinc square, and for the impulse function which is at 0 we will get the constant value. So at 0 we will get 1 plus f naught into sinc 0, and the sinc 0 is always equal to 1. Sinc 0 is always equal to 1. So sinc square is also 1. So 1 plus f naught, and the value of f naught is given as 0.5. So we will get Rx of 0, which is 1.5. Now Rx tau at tau tends to infinity. So the value of sinc at infinity, this is 1 plus limit tau tends to infinity f naught into sinc square f naught into tau. So the value of sinc, the sinc function will be like this, the sinc square function will be like this, because this is sinc square, we will not get the negative value, you will get the positive value only, and this is the tau, and this is sinc function, sinc square function, sinc square function. So at tau tends to infinity, it is towards 0. So at tau tends to infinity, this term will be 0. So this term will be 0. So you will get 1, that is nothing but mean whole square or DC power. So the DC power is 1 and the total power is 1.5. So the AC power is total power minus DC power. So the total power is 1.5 and the DC power is 1, you will get 0.5. Yes, you can calculate its area and you can get the Rx of 0, that is the nothing but this third property of the power spectral density, which is area under the power spectral density gives the total power. But to calculate the mean value or to calculate the DC power, the correct way to calculate the DC power is, if you calculate the autocorrelation and substitute tau tends to infinity, you will get the correct value of mean or the DC power, because sometimes we say that at f equal to 0 whatever will be the value, that will be the value of mean, but sometimes it may give you the wrong answer. In some question it may follow the same thing, but in few questions it may give you the wrong answer. So for that, the better practice would be, if you want to calculate the mean value from the power spectral density, then first calculate the autocorrelation for the given power spectral density and substitute tau tends to infinity, then you will get the correct value of mean. In the previous gate questions, you can see that there are two questions for which you may get confused if you calculate the DC power saying that at f equal to 0, because the frequency is 0, that means the DC signal, so near about f equal to 0 you will get the DC power, but sometimes it is a confusion for you, okay, because at f equal to 0 you are having the 1. So you may say like this, but that will not be a good practice. If you want to calculate the mean value, always calculate it from autocorrelation. Okay. So coming to the next question. So next is question number 7. Question number 7. Question number 7 is, a noise process has a power spectral density given by Sn of f 10 to the power minus 8 1 minus mod f divided by 10 to the power 8 mod of f less than equal to 10 to the power 8 and 0 when mod of f greater than 10 raised to power 8. This noise is passed through an ideal band pass filter with bandwidth of 2 megahertz centered at 50 megahertz. The power content of the output process is. So, Akansha, today's question is question number 12. We are having the 12 question up to question number 12. So, we are in the 7th question. It will take around half an hour to get to reach to the 12th question. Maximum. We may solve it. If you guys solve it fastly, then we can reach to the 12th question very soon. Rajneesh Patel, solve this question 7. So we are having the 7th question, and the 7th question is the power spectral density is given. So if we solve, if we draw this power spectral density, so this is the standard expression for the triangular signal, which is having the height 10⁻⁻8 and the slope you can calculate. So if I draw it, this is SNF, and at f equal to 0, if you substitute f equal to 0, you will get 10⁻⁸. So this is 10⁻⁸, and if you substitute, you can see that the mod of f less than equal to 10⁸. So if you substitute f equal to 10⁸, so 10⁸ and 10⁸ will get cancelled. So 1 minus 1, that will be 0. It means at 10⁸ it is going to be 0. So this is nothing but the standard expression of triangular signal. This is f. Okay. So suppose I write it in megahertz. If I write it in megahertz, then this 10⁸ become 100, because 100 into 10⁶ is 10⁸. Okay. So this is minus 100. This is 0. Now this process is passed through a band pass filter. The filter which is center about 50 megahertz and bandwidth is 2 megahertz. So this is axis is also I am taking in megahertz. So the band pass filter will be like this. It is centered at 50 and this bandwidth is 2 megahertz. So this is minus 50 and again this bandwidth is 2 megahertz. So this is the response of the filter, because this is in megahertz and the bandwidth is 2. So that means if you want to draw the response of the band pass filter, so whatever will be the bandwidth, divide it by 2 and add that to the center frequency and subtract from the center frequency. So if I divide it by 2, we will get 1. So add with the center frequency, so 50 plus 1 we get 51 and subtract 1 from 50, that is 49. So you get 49 to 51. So this is also minus 51 and minus 49. So this is how you get the 2 megahertz bandwidth. Now this is this power spectral density is passed through this particular band pass filter, and you have to calculate the power of the output of this band pass filter. So if I define, as you can see that this is up to the 100 megahertz, the input to the power spectral density is up to input to the band pass filter is extended to the 100 megahertz, but this will pass only from the range 49 to 51 megahertz. So we can write the output power spectral density is equal to, from this property h of f magnitude square and input power spectral density Sn of f. So this would be, because this is limited to the 49 to 51, this Sn of f, which was previously mod of f less than 10 to the power 8, now it will be in the range of 49 to 51 megahertz. 49 to 51 megahertz. Is it clear? Because from 49 to 51, somewhere here 49 to 51, this portion of the noise will pass through the filter. This portion of the noise will pass through the filter. This one. Suppose this is 49 to 51. So only this part of the input noise process will pass through the filter, and other will be rejected by the filter. So this is how we can write mathematically. So 0.05 Akansha is getting, but this is not the correct answer. 0.0206. From mean square value we can calculate the power. Mean square value is actually equal to the total power. Okay. So let's solve this. If I calculate the area, okay, so if I calculate the area, we get the power, and area is minus infinity to infinity Sn naught of f df. This is the area of the output power spectral density. Output power spectral density. So now the power is equal to integration from, because this is a even function, so you can also write like this, 2 times 0 to infinity Sn naught of f df. So you will get 2 times 49 to 51. This is in megahertz. Okay, so 49 into 10 to the power 6 into 51 into 10 to the power 6, and Sn of f, and that is for the positive value, because we have converted the limit in the positive value. So the value is 10 to the power minus 8. So we get 10 to the power minus 8, 1 minus f of divided by 10 to the power 8 df, because we are having the positive value. So the mod of f will be positive. So now if we integrate it, we get 10 to the power minus 8, you get f, limit from 49 into 10 to the power 6 to 51 into 10 to the power 6 minus 10 to the power minus 8 divided by 10 to the power 8 f square divided by 2, limit 49 into 10 to the power 6 from 49 to 51 10 to the power 6. So if we solve this, so we get 2 into 10 to the power minus 8, this is 51 and 49, that is 2 into 10 to the power 6, minus this will be 10 to the power minus 16 divided by 2, and this will be 51 square minus 49 square, and this is 10 to the power 6 square, which is 12. So this will be 4 into 10 to the power minus 2 minus 51 square minus 49 square. How much you are getting? This is I think it is 200. Let me check. So we are having the value as 2 into 10 to the power 2 into 10 to the power minus 16 into 10 to the power 12. So solve this. If is there any mistake, then you can tell me. Okay, so 200 you are getting. So this is 2 into 10 to the power minus 2. So this is 0.02 watt. Okay, so this value is after the whole calculation, we will get this value. Okay, so not a 20 milliwatt. Okay, so 20 milliwatt you are getting. Okay, so I have asked in watt, so the answer will be 0.02 watt. 0.02 watt will be the right answer. Okay. So is it clear to you? Is there any doubt in this question? you can tell if you find any difficulty in any step, then we can discuss it now. Okay. So let's move to the next question. Explain integration part. What is the problem in the integration? What is the problem in the integration? Can you tell me? Because this is constant one, so if you integrate, you will get f, right? And I have multiplied it this 10 to the power minus 8 inside. So the integration of f is square by 2. So this is 10 to the power minus 8 divided by 10 to the power 8, and this is f square by 2. So if I substitute the limit, this is 51 into 10 to the power 6 whole square. So 51 is square, and 10 to the power 6 whole square is 10 to the power 12. And minus the lower limit, which is 49 into 10 to the power 6 whole square. So this is 49 square into 10 to the power 12. I have taken common. So by calculating, you will get this value, and after solving, you will get 0.02. Okay, I will share the questions in the Telegram group. Okay, so the questions we are discussing right now, I will share all the questions, PDF of the question in the Telegram group. Next is question number 8. Question number 8 is, which of the below are not autocorrelation function of wide sense stationary random process? Which one of the following are not the autocorrelation of wide sense stationary process? So we are having the property of autocorrelation. The function which follows the property of autocorrelation will be the valid autocorrelation, else it is not. So answer we are getting as A, C. Result, which result function of tau, Ketan? Result is function of tau. If you calculate the autocorrelation of any process, and if it is a function of tau and its mean is constant, then we say that that process is wide sense stationary. So you are saying that if the result is function of tau, that means if the autocorrelation function is function of tau, then it is a wide sense stationary. Yes, but provided that the mean should also be constant. Mean should also be constant. So the correct answer, let's move to the question. The correct answer is option D. Yes, option D is the correct answer. As you can see that we are having the first autocorrelation R of tau is sine of 2 pi f naught tau. Okay, so sine is actually a odd function, because if we calculate R of minus tau, we get sine of minus 2 pi f naught tau, which is minus R of tau. So it is not following the even symmetry. Hence, cannot be a valid autocorrelation. Got it? Now, the second one, this is the first one, so it is not a valid autocorrelation. Now, the second one is R of tau is equal to tau square. So, if you calculate R of minus tau, you will get minus tau whole square. So, that means you will get tau square. So, you will get R of tau. So, it is following the even symmetry. Okay, but only from the one property we cannot judge the answer. So, there is another property which is R of 0, R of 0 is 0 and R of 2 suppose is 2 square, that is 4. So, here R of tau is greater than R of 0, R of tau is greater than R of 0, because we know from this property that Rx of tau should always be less than or equal to Rx of 0. So, if we substitute the value of tau, we should get the value less than equal to the value which we got for tau equal to 0. So, for tau equal to 0 we are getting 0, but for tau not equal to 0 we are having the value greater than 0. So, that is why it is not following the second property of autocorrelation. So, it is also not a valid autocorrelation. Okay. Now, for the third one, if I calculate Rx of 0, we get 1. If I calculate Rx of 1, then we get 2. Again, Rx of 0 is less than Rx of 1, hence not a valid autocorrelation. So, all the three are not a valid autocorrelation. So, according to this, the correct answer will be option D. All the autocorrelation functions are not a valid autocorrelation. Is it clear? Next is question number 9. Next is question number 9. X of t is the random process given by x of t equal to x plus y, where x and y are independent and x is uniform on the interval -1 to 1 and y is uniform on 0 to 1. The power spectral density of the random process x of t is. X of t is the random process given by x of t equal to x plus y. Answer is C, A. Again, answer is coming as C. Check once again till others solve the question. We are waiting for the others to answer. So till then you can check the answer whether you are getting the correct answer or not. You can check your calculation. Till then we can wait for others to answer. So do you guys share this about this session to the friends or your classmates? Because if you are having you are getting the advantage from the session, then you can tell your friends to attend this session, so that the maximum students will be participating, so the more competition will get. How fast all other students are solving, that we should look for, because that will be give you the environment of the competition, so that you can solve the question fastly with the temperament that the others are also solving with you, and you have to answer fastly than them. So answer is 4/3 delta f. So answer C or B, C or A I am getting from the most of the students. Question not visible. Okay, you might join the late, that's why you are not able to see the question, because others have solved the questions. Let's solve the question and then you can join from the next question, Prince. So we are having the x of t as a random process. X of t is equal to x plus y. We want to calculate the power spectral density. So let's calculate the autocorrelation, because the Fourier transform of autocorrelation function is the power spectral density. So let's try to calculate the Rx of tau. So by definition, this is expected value of x of t and x of t plus tau. Okay, so this is expected value of x of t is x plus y and x of t plus tau, because this is independent of time, so this is nothing but x plus y only. X plus t plus tau is also x plus y. So we are having expected value of x square plus 2xy plus y square, and this is expected value of x square plus 2 times of expected value of xy plus expected value of y square. Because this x and y are independent, so if the two random variables are independent, then the correlation between the x and y can be written as expected value of x multiplied with expected value of y. Likewise, probability, in probability of joint event AB, if these two events are independent, then we write probability of A into probability of B. Similarly, expected value of x, y, if x and y are independent, we can write expected value of x multiplied with expected value of y. So this is how we can write. Now it means that to get the value of autocorrelation, we have to calculate the mean square value and mean value of x and y both. So we know that if there is a random variable x which is uniformly distributed between A and B, then its mean is A plus B by 2, its mean square value is B square plus AB plus A square by 3, and its variance is B minus A whole square by 12. Okay. So if I calculate for x, so expected value of x, because x is distributed between -1 and 1, so this is -1 plus 1 divided by 2, so this is 0. Expected value of x square, the value of b is 1 and the value of a is -1. Okay, so the first value is a and the second value is b. So -1 to 1 it is given. So this is 1 square minus 1 plus 1 square, and the b is 1 and this is -1 square, okay, divided by 3. So you will get 1 by 3. Similarly, expected value of y, a plus b by 2, so this is 0 plus 1 by 2, you get 1 by 2, and expected value of y square, b is 1, a is 0 into 1 and 0 square divided by 3. So you will get 1 by 3. So this is the value of mean and mean square value of x and y. So expected value of x square, you have got 1 by 3. 2 into mean value of x, you are getting 0. So that will be 0. And mean square value of y, you are getting 1 by 3. So that means we are getting as 2 by 3. So the autocorrelation function is 2 by 3, and from the property of the power spectral density or the Wiener-Khinchin relationship, from Wiener-Khinchin relationship, we know that the power spectral density or the autocorrelation are Fourier transform pair. So if I calculate the Fourier transform of 2 by 3, I get 2 by 3 delta f. So according to this, the correct answer will be option D. Okay. So is there any doubt in this question? If you are facing any difficulty in this question, then you can ask. So why were you getting the answer as A or C? That you can see what was the mistake you were doing. What is the difference between power spectral density and periodogram? This I can answer you when I will teach the power spectral density theoretical part. Because there is a deep concept behind the periodogram, so that's why we cannot discuss it here right now, because we are running out of time. Thank you, Nilkamal. Next, let's solve question number 10. We'll tell you very soon in the maybe in the next session or in the coming session, Vishnashan. So don't worry about this. I will tell you the difference between these two. Question number 10. The theoretical part of the random process you will not get in our channel, because I have not discussed any theoretical part in our channel. For that you can follow our PD course. If you have not purchased it yet, so you can buy it, or you can follow any textbook to get the communication part. Okay. Rahul, which semester you are right now? Are you a college going student? Are you a second year student or third year student? So accordingly I can suggest you how you can start preparing communication system. And if you are if you have joined any coaching institute, then also you can tell me. So final year students you are, and have you joined any coaching institute for the GATE or ESE? Ketan is getting 4.74. A zero mean WSS process. That means we are having a random process x of t which is having a zero mean, and the power spectral density of this process is 2 upon 1 plus omega square. So from the Wiener-Khinchin relationship, if I take the Fourier transform, inverse Fourier transform of the power spectral density, I will get the autocorrelation, and this is written in this form 2 into 1 upon 1 square plus omega square. And previously we have seen that the Fourier transform of e to the power minus a mod tau, Fourier transform of e to the power minus a mod tau is 2a upon a square plus omega square. So on comparing these two, we have the value of a as 1, so the autocorrelation is e to the power minus mod tau. So if you are having the if you are self-study student, then you can follow any standard textbook or any standard notes from any other coaching institutes and follow the theoretical part. So Rx of tau is equal to e to the power minus mod tau. Now what we have to calculate, we have to calculate the variance of yt. So it is given that this y of t is equal to summation k equal to 0 to 2 x of t plus k. So if I substitute the value of k, I will get x of t plus 1 and x of t plus 2. So this is the process we are having for which we have to calculate the variance, and we know that the variance of any process can be calculated by mean square value minus mean whole square. So that means we have to calculate the mean value of yt. So what is the value of mean value of yt? So expected value of yt is expected value of x of t plus x of t plus 1 plus x of t plus 2, and this is expected value of x of t plus expected value of x of t plus 1 plus expected value of t plus 2, x of t plus 2, and the expected value of x of t is given as 0. So this is 0. What about this expected value of t plus 1? Because it is given that this x of t is a wide sense stationary process, the mean value will not change with time. So if t plus 1, the mean value will remain constant. So at t plus 2 also the mean value will be constant. So the mean value will be 0. So if the mean is 0, if this mean is 0, the variance will be equal to the mean square value. So let's calculate the mean square value. So mean square value of yt, mean square value of yt is expected value of y square t, and this is expected value of x of t plus x of t plus 1 plus x of t plus 2 whole square, and this is a plus b plus c whole square. So we can write expected value of x square t plus expected value of x square t plus 1 plus expected value of x square t plus 2. This is a square plus b square plus c square, okay, and this is 2 times of 2ab, that is x of t and x of t plus 1, and this is 2 times of expected value of x of t plus 1 and x of t plus 2, and 2 times of expected value of x of t and x of t plus 2. So this is mean square value of input. Mean square value of input means at tau equal to 0, because we are having the Rx tau. We are having Rx tau, so we can calculate the mean square value of x. So mean square value of x is nothing but, this is nothing but Rx of 0, and with respect to, because this is a stationary process, with respect to time, the mean square value will also not change. So this is also Rx of 0, this is also Rx of 0. Okay, so these all three terms are autocorrelation at tau equal to 0. This is 2 times of the difference between these two. The difference between these two is 1 second, so that is Rx of 1. So the delay of these two processes is 1. So this is Rx of 1. So delay between these two is also 1. So this is 2 times of Rx of 1. So the delay between these two processes is 2. So this is 2 times of Rx of 2. So we have got 3 times Rx of 0, 4 times Rx of 1 and 2 times Rx of 2. So Rx 0 e to the power 0, that is 1. So we get 3 plus 4 times of e to the power minus 1 plus 2 times of e to the power minus 2, and after solving this you will get 4.74. Okay, so this will be the answer, 4.74. Okay, so have you got the answer or any doubt in this step? If there is a stationary process, then the mean square value will be constant, that will not change with respect to time. And because the mean value of yt is 0, since this mean value is 0, the variance of y is equal to mean square value of y minus 0, and that is 4.74. Okay, because the mean was 0, that's why mean square value is the variance, because in this question we have to calculate the variance. Okay, so it is not given that they are independent. Okay, so this x of t and x of t plus 1 and x of t plus 2 are not independent from each other. If they are independent, then we can say that the variance of x of t, variance of t plus 1 and variance of t plus 2 will be addition of the variance of y. Okay, because the property you are talking about, Anand, is only for the x and y are independent. Because in this question it is not given they are independent, so you cannot apply that property. So let's solve question number 11. Question number 11 is, let x of t be a wide sense stationary random process with autocorrelation Rx of tau a e to the power minus alpha mod tau. The second order moment of the random variable of x of 5 minus x of 2 is. So in this question, second order moment, what is second order moment? second order moment is nothing but mean square value. Second order moment is nothing but mean square value. So expected value of, we have to calculate mean square value of x of 5 minus x of 2. So we have to calculate the mean square value of x of 5 minus x of 2. So we have to calculate the expectation of square of this random variable. So x of 5 minus x of 2 is square and expectation. So we get expected value of x square 5 plus expected value of x square 2 minus 2 times of expected value of 2 and expected value of 5. So same as the previous question, it is nothing but the mean square value of x, and because the autocorrelation is given, the mean square value of x is nothing but at tau equal to 0. So this is Rx of 0. So and also it is given that the x of t is a White-Sands stationary. So with respect to time, there will be no change in the value of mean square value. So x square 5 and x square 2 will be same. So that is also Rx of 0 minus 2 times of, this is expectation x of 2 and x of 5. The difference between these two is 3. So that is the autocorrelation function of 3, the time delay. So Rx of 0 is A, Rx of 0 is again A, and Rx of 3 from the expression of Rx tau, when we calculate, this is 2A e to the power minus 3 alpha. So when we solve it, we get 2A minus 2A e to the power minus 3 alpha. So when we take this 2A common, we get 1 minus e to the power minus 3 alpha. So according to the options, the correct answer is option D. Okay, so if you have got the answer, option D. Okay, so I will share the PDF in the Telegram group. So we are having the next session from the 9 p.m. So that's why we are ending up this session, and I will come with the next session. Maybe it is possible that that the topic will be from EMT, okay, or if it will be from the communication, then the next chapter we will start is amplitude modulation. I hope you have enjoyed this session. Thank you. Good night.